testing now. Okay. Okay, so am I good to start?
Yeah, just switch on the presentation mode. Perfect.
Yes, yes. So let me know if you can't see this, but I imagine you can. And can you see my mouse so I can point to some things?
Yes.
Okay, great. Okay, well, thank you everyone for coming to my thesis presentation titled A Hierarchical Pedestrian Behavior Model to reproduce realistic human behavior in a traffic environment. Let's get started. So the motivation for this work at a high level is to help create safer interactions between autonomous vehicles, or in general, autonomous systems, and pedestrians. As pedestrians are the most vulnerable road user, any misinterpretation of their intentions or their actions could lead to severe consequences or even fatal consequences. So this is where scenario-based testing comes in. So scenario-based testing in a simulation environment is a safe and efficient way to thoroughly test AVs or any autonomous system. So a common goal in the scenario-based testing process is to generate critical scenarios to be able to test the autonomous system on and test its responses to these scenarios. And these scenarios, critical scenarios, can be difficult to find in existing data and obviously dangerous to test outside of a simulation environment. So our work provides specifically goal-oriented scenarios in which the tester can define a goal that they want to achieve, that the scenario needs to achieve in order to test the autonomous system. And this goal can help create these critical scenarios by forcing the system into certain situations. As a simple motivating example that we have on the bottom here, we have one pedestrian represented by the dot and one vehicle, the rectangle. And the pedestrian needs to cross the crosswalk, and the vehicle is crossing over the crosswalk. And the goal of this scenario is for the pedestrian to create a collision with the vehicle on the crosswalk. And so the key point is we want this goal to be achieved no matter what the starting state is. So you can change the starting positions of the agents, their starting velocities. No matter what, we always want this goal to be achieved and this situation to be produced. So contributions of this work are split into two sections. The first being we present a novel hierarchical model for pedestrian motion simulation. And we use at a high level, we use behavior trees to provide highly controllable and customizable decision-making processes. And at the lower trajectory level, we produce realistic motion with an adapted social force model. And along with this model, we provide a catalog of pedestrian maneuvers and decisions. And these maneuvers and decisions are what compose the behavior trees, which we'll get into on a later slide. So the second part of these contributions is the evaluation of this model. So we evaluate on two different trajectory data sets that have different road structures. And we want to measure the decision-making realism and the motion fidelity of the model. So through this evaluation, we show that the high-level decisions of the empirical pedestrians, so the real-world pedestrians, our model replicates these decisions with a 98% or better accuracy, and it also reproduces the motion trajectories, the low-level trajectories, with an average deviation of 1.36 meters. So jumping into the model, this is a high-level overview of the model's structure and some of the information flow between the different components. So I'll draw your attention to the right-hand side. I mentioned it's a hierarchical model, so we have these three ordered hierarchical layers that feed into each other and help them that compose the model. So at the top layer, we have the behavior layer. So this is what receives the test scenario goals and any of the configurations of the behavior trees and maneuvers. And its role is to receive those and select a maneuver that's going to be executed by the pedestrian at a lower layer. So this is the decision-making part that selects what maneuver to carry out at every time step of simulation. So this maneuver is passed to the next layer, the maneuver layer, whose job is to take that and translate it into instructions on how the pedestrian should change their trajectory. And then finally, these instructions are passed to the low-level motion planner layer, which incorporates a social force model, an adapted social force model to produce the pedestrian's next state information. So we have this process flow from the high-level goals all the way down to the next state information that needs to be updated in the simulation. On the left, every component, every layer of this model has access to this traffic state estimation, which is basically just a snapshot, a ground truth snapshot of a representation of the road and the dynamic elements in the traffic, as well as some mapping information. So we'll elaborate on that here. So the point of this traffic state estimation is to simplify the environment around the pedestrian into interpretable and relevant information. So this information includes all the states of dynamic elements, including the vehicles and other pedestrians, their state information, as well as the states of the traffic lights and, if it's relevant, the pedestrian crossing signals for the crosswalks. And the last part of this traffic state estimation is the lanelet2 map file, which we see on the right-hand side here. Lanelet2 is a helpful library to help define the structure of the underlying map, and also provides helpful functions for the agents to navigate through this structure, both vehicles and pedestrians, to navigate through the traffic environment. So the first step of the process starts with the behavior layer. So as I mentioned, the role of this layer is to take the traffic state estimation and all the configurations of the behavior trees, and using a behavior tree, decide what maneuver should be executed down the line at the lower layer, at the lower layers. So we will see, I'll go through a brief overview of behavior trees, and we'll go through a quick example of how this process works. The behavior trees they explicitly represent the behavior and the decision-making processes. And each pedestrian in the model runs their own instance and has their own personal behavior tree. So it's not necessary that all the pedestrian agents in the simulation are following the same decision-making process, as they might have different trees that dictate their maneuvers and how they come to those maneuvers. So I'll briefly go through the composure of the behavior trees. So the internal nodes are made up of either selector or sequence nodes, shown by a question mark or an arrow. This is within the scope of our work. We have these two kinds. There are extensions of this with parallel nodes and other nodes, but within our scope, we have these, and these control the flow of the information as the tree is being traversed. And then the leaf nodes of the trees are the maneuvers and the condition nodes. So if you see on the right side, we have condition nodes as the diamonds and maneuvers as the ellipses. So these leaf nodes, after they're evaluated, they return a return status, and the status can either be success or failure or running. And these statuses help the internal nodes, the selectors and the sequences, to dictate the flow, to know what node to visit next. So briefly, again, the selector nodes can be thought of as sort of like a logical OR, where they continue, or they sequentially visit their children nodes from left to right until a status of success is received, at which point they return to their parent. And on the other hand, sequence nodes visit their children from left to right as long as success is received. So until a status of failure is received. And yeah, so I'll go through a quick example. So this is a behavior tree that a pedestrian could use after they've decided to cross a crosswalk, but now they have to make the decision on when to enter the crosswalk based on the crossing light state. So we start in a depth first fashion, going all the way to the leftmost leaf node. And this is a condition node that checks if the crossing light is green. If it is green, then this node returns a success. And since this is a sequence, when it receives a success, it goes to its next child, which is goes to the maneuver node, enter crosswalk. And that returns a success all the way back up to the root. And since this is a selector that received a success, it's done. It returns from the whole tree, and the maneuver that was last visited by the tick, by the traversal, is then selected to be executed. So it would select to enter the crosswalk. Now, on the other hand, if the crossing light isn't green, if it's yellow or if it's red, then it returns failure. And since it's sequence, it returns failure back up to the root, travels over to the other option, the other maneuver, which is wait at the crosswalk entrance, which returns success and ultimately is the maneuver that's selected. So that's a quick, simple example. At the bottom, we have the text representation of that. It's just an example of the text file that the model actually uses. So these behavior trees can make it easy to inject intentional desired behavior into the scenario without needing any specific technical knowledge on the technical details of the model. You can use this catalog of, I think that's next one. Yeah, you can use this catalog of maneuvers and conditions to compose all sorts of different behavior trees that produce different behaviors. So this is a list of the currently implemented maneuvers and conditions, and these were developed iteratively through our evaluation process. And so these were composed on our evaluation data sets. And so obviously these can be extended if the simulation model requires it, but these are the currently, and we can return to this if anyone has specific questions or wants to revisit any of the specifics on the maneuvers or conditions. Sorry. So we started with the behavior layer and we selected a maneuver to be executed, and that maneuver is passed to the maneuver layer. And the role of this is to receive that maneuver and translate it into a three-part instruction on how the pedestrian should adapt their current trajectory. And these instructions should be relevant and interpretable by the next layer, the motion planner layer, which has the social force model in it. So these three instructions that's translated into can be a new waypoint, a new direction vector, and a new desired speed. So briefly, I have a waypoint example on the right-hand side here in the figure, because if you have a somewhat complex traffic environment like it's shown, it's not sufficient to pass the final goal point, which would be 0.5, to the motion planner layer, because there are intermediate points that the pedestrian must visit before even considering that point. So that's where waypoints come in, where it's an intermediate point that the pedestrian needs to visit, and it's passed to the motion planner layer. And obviously a full pedestrian journey can be composed of multiple maneuvers, which produce multiple waypoints as seen in here. Okay. So the last layer in this process is the motion planner layer. So this incorporates an adapted social force model to receive those 3-part instructions on how to adapt the trajectory and process them into the next state information for the pedestrian. So the next acceleration, velocity, and position of the pedestrian for the next simulation cycle. And we'll go through details briefly of the social force model. So the social force model works on the principle that human motion is based on attractive and repulsive forces. So we have 3 main collections of forces. The first and only attracting force is attracting the pedestrian towards their goal point. We call that F adapt. And this is where the waypoints are important, because we can't, if you remember the previous diagram, we can't simply walk directly towards our final destination. There are intermediate points in between need to be visible. And the second collection is repelling forces from other agents, so other vehicles and other pedestrians. So they have repelling forces to represent the tendency to not get too close to other pedestrians and not collide with other agents. And finally, the third collection is the border forces or the wall forces. So they're repelling forces away from the physical walls and borders of the environment to make sure the pedestrian respects them and doesn't collide with them like the other repelling forces. So now to the evaluation portion of the model. So the evaluation was driven by the 2 research questions that wanted to answer how realistic are the low-level movements and also the high-level decisions made by these simulated pedestrians with respect to the empirical pedestrians of our data sets. And so for the first question, measuring asking about the realism of low-level movements, we measure the trajectory realism by the average and the maximum Euclidean distance metric. And also we measure the path realism by the Frechet and Hausdorff distances, which are more geometric similarity measures for the entire path. So the second research question deals with how realistic are the high-level decisions. And so we just measure this by accuracy. So we need to define a process. Well, first, we evaluate our model on 2 separate dataset locations with different road structures. So the first is a busy 4-way intersection with traffic lights and 6 different crosswalks. And the second is an unsignalized crosswalk at the University of Waterloo. So a lot fewer cars in the second one, but a lot more pedestrians. So we need to define a process to measure our simulated pedestrians against the real world pedestrians. So we set up these evaluation scenarios in which, in a given dataset recording, we select one real world pedestrian to remove from the scenario and replace it with one of our simulated pedestrians running the model. And then all the other agents are left as they are, and they follow their empirical trajectories from the dataset. And so we want to observe if the model pedestrian A makes the same decisions as the pedestrian it replaced, and also follows the same low-level path. We have those 2 phases of the evaluation. And so the last part of the evaluation is relevant for the intersection data set, where we noticed that the evaluation scenarios had an average length of over a minute, which were fairly long scenarios. And what happened was there was an accumulation of error throughout the scenario. So a small deviation in the beginning could accumulate into a large deviation at the end of the scenario, which wasn't necessarily representative of the model's performance at the end of the scenario, and was instead due to an earlier error. And so to mitigate this, we took the full intersection dataset scenarios, evaluation scenarios, and chopped them up into segments. So each segment defined its own individual evaluation scenario, and these segments represented a portion of the pedestrian's journey. So this could be a single stretch of sidewalk or crossing a single crosswalk. So this helped mitigate that long-term deviation. So with respect to the development of the pedestrian behaviors, I mentioned before that the maneuver and condition catalog was developed iteratively through multiple phases. And it was done using the intersection data set. And then once that phase of the model was stable, we tested the extensibility and the generalization of the model by applying it to the second location, which is the unsignalized crosswalk, without making changes to the model to test how well it generalized and if it could get the same results on a different data set. And it was shown to perform well. So visually, this is 4 examples of 4 different evaluation scenarios. The top 2 are on the intersection data set, and the bottom 2 are on the single crosswalk. So we can see here the dotted blue trajectory is the empirical trajectory from the data set, and the solid red is the generated trajectory from our model. So this kind of gives you an idea of how the results look. So in terms of the first measurement, measuring the low-level trajectory matching, so we used, as I mentioned, the metrics, the Euclidean distance, Frechet distance, and Hausdorff distance to measure both the accuracy of the time-based trajectory with the Euclidean and the geometric similarity between the paths using the other 2 measures. So we see the results in the tables here, where for the intersection data set, we have both full and segmented scenarios. And as you can imagine, the segmented scenarios improved. I mean, it generated a lot more scenarios, and it improved the each metric value considerably due to them being shorter, and also the model pedestrian getting reset to the empirical data at different points of the journey. And generalizing to the single crosswalk data set, we can see that there's an even further improvement and a much larger number of scenarios, further improvement to the values for the intersection data set. So while those results were reasonable, we wanted to identify points of high error throughout the pedestrian's journey. And through observation, through multiple phases of evaluation, we noticed that most of the time, even, pedestrians in the real world employ this corner cutting behavior at crosswalk entrances and exits. So they don't always, if they're entering a crosswalk, they don't always go directly to the crosswalk entrance, and same with exiting. They don't go to the exit. They display this corner cutting and more natural entrance and exit of the crosswalk. So these were points of high error because it would take different amounts of time to enter and exit crosswalks, and there would be a delay, and error would accumulate as a result. So we were able to identify these, and on a case-by-case basis, develop a process to, so we adapted the maneuvers for the entering crosswalk and the exiting crosswalk to optionally allow this corner cutting behavior for the simulated pedestrians. So now the second part of the evaluation is measuring the high-level decisions. So basically here we're asking, do the simulated pedestrians make the same decisions as their empirical counterparts, the empirical pedestrian they replaced? And so to measure this, we define two distinct decision points. The first being, given multiple crosswalks, so as the pedestrians approaching the intersection, so this metric or this evaluation was only performed on the intersection data set, just due to the oversimplified structure of the second data set. So this is all in the intersection. So given, as you're approaching the intersection, given multiple crosswalks that the pedestrian could take to go towards their destination, which crosswalk do they take? And we measure, or we check if the simulated pedestrian takes the same crosswalk. And also, after choosing this crosswalk, and it displays a non-green crossing signal, so it's either red or yellow, will the pedestrian begin to cross, or will they wait until the next green state cross? So after this evaluation, for decision one, we showed that our model pedestrians picked the same crosswalk 100% of the time. And for the second decision, there were 3 instances of the model pedestrian entering the crosswalk at a different time than the empirical pedestrian. So we investigated these, and it turned out to be a situation, all 3 of them were an identical situation that wasn't yet covered, but could be covered by an extension. So this was when the empirical pedestrian waited for most of the red light, most of the red crossing signal. But then when there's a 2-way advanced green for the vehicles, the pedestrian only waited until there were no more conflicting left-turning vehicles before entering the intersection or entering the crosswalk, even though the crossing signal was not yet green. So again, this wasn't yet covered, but it could be covered by an extension to the maneuver and condition behavior tree nodes, including a behavior, or namely a behavior, where the probability of entering the intersection, entering the crosswalk, increases with waiting time, which is what was displayed by the empirical pedestrians. Some of the limitations of our work, research scope wise, our work was primarily focused on replicating the human or the pedestrian behaviors in motion, given the data sets that were available to us. And then the next step of this for future work would be to apply this model and refine this model in the context of scenario-based testing. So it sets up nicely a process for scenario-based testing, but the next step would be to apply this. And some specific notable model limitations. Obviously, we're limited by the coverage of the maneuvers and conditions, since they were developed and refined by the data that was available to us. A different data set or a different scenario may require new maneuvers and conditions that aren't included in our work yet. Another notable limitation and potential extension would be this hierarchical group dynamics that currently isn't shown with our pedestrians. So this can either be handled at the social force model level. So there are existing social force model variations that include group dynamics and subgroup dynamics, or it could also be incorporated into the higher level behavior tree component of the model. And finally, notable limitation of the model is our point mass representation of pedestrians. So we abstract away the static and dynamic body poses, which could be relevant information for autonomous vehicles or drivers in general. We simply have a point mass model for pedestrians. But again, this can be future work and an extension of the model to incorporate these body poses and maybe even develop new maneuvers based on the body poses, such as crouching or something like that. And as I mentioned before, the evaluation limitations were limited by the available data that we have and the amount of data we have. Over 1,400 pedestrian agents and over 3,800 vehicle agents, but of course, we're limited to the available data. So yeah, expanding that availability would provide more opportunities for extension. So to wrap up, some conclusions and future work, we presented a novel hierarchical pedestrian simulation model that uses behavior trees to handle high-level decisions and that inform a low-level motion planner as driven by the social force model. And our evaluation process shows that this model can replicate realistic behaviors and actions in a traffic environment. And our model lends itself well to scenario-based testing in that testers can easily inject desired actions and behaviors into scenarios using behavior trees, the explicit representation nature of behavior trees. And they can use this process to generate realistic, but possibly critical or dangerous scenarios that are difficult to find in data and obviously dangerous to test outside of a simulation environment. So in terms of future work, again, addressing the scope, model, and evaluation limitations from the previous slide. And also an interesting future work direction would be to automate the creation of these scenarios from data. Automate that process, automate that process. And then those scenarios can even be manipulated further by the testers. So I will finish off with some example videos. Hopefully they're clear enough. I know they're blown up quite a bit, but we'll go through and feel free to interrupt and ask questions if something's not clear. So I'll do my best to pause it every so often and give an update on the light states. I know they're not always easy to see. So in this first scenario, this is on the intersection. We have one pedestrian in the bottom corner here, the dot, and their goal is across the intersection in the top right corner. So they will plan, let's see if I can, there we go. They will plan a path and let me pause that. So this light, sorry, it's hard to, this light refers to this crosswalk going here, and these diagonal lights refer to these more horizontal crosswalks. So right now the vertical crosswalk is green, so it will opt to enter it and take it. Obviously, it needs to cross multiple crosswalks in order to reach its goal. So it stops at the entrance of the horizontal top crosswalk because the light, this light here was red, and now they go when it's green. And these triangles are traffic islands in the scene. And then these connecting crosswalks are unsignalized, so the pedestrians have right of way and they cross over the right turn, I think slip lanes, the merge lanes for the intersection. So that was a very simple example. We'll see. There we go. This is what I want. We'll see a slightly more involved example, just with 3 pedestrians, but again, similar. And I've added a vehicle in here. I've just manually forced it to stop within the crosswalk to show how the pedestrian walks around a vehicle obstructing its path. So again, P2, pedestrian 2 and pedestrian 3 have to wait at the red light for it to be green and travel towards their respective goals. So the handling of, you'll see P3 interact with the vehicle. The handling of this is done at the social force model layer with the vehicle forces that I showed in the slide, the previous slide. And now we'll look at the scenario that I talked about in the beginning, where the goal of this scenario is to create a collision. So the pedestrian P1 is only one of them. Its goal pointed across here, but its main goal is to, or the goal of the whole scenario is to create a collision with the vehicle at the crosswalk. Sorry, I know that's light to see at the crosswalk here. So we'll see it dynamically change its speed so that it jumps in front and ultimately gets hit. So, and as I mentioned, the goal of this is to make sure that that collision happens no matter what the setup is. So, so now we have the same scenario goal, but I've changed the position of the starting positions of vehicles, or of the agents, and also the direction of the vehicle. We can see that with only those changes, no changes to the model, it still gets hit on the crosswalk of the vehicle. That's a key point. That concludes the presentation portion. Thank you very much for listening.
Awesome, thank you. So I guess we can have some questions now.
Should I stop the recording or get the questions?
Yeah, let's stop that. Yeah.
Okay. There it is.